Hello everyone, welcome back to the physics lesson. If you like the topic, hit the like button and have any comment, leave in the comment box. I'm trying to improve the content of the video in the next. So to begin with, today we are going to discuss with the Coulomb's law, the relative permittivity or dielectric constant, the continuous charge distribution, linear charge density, surface charge density, volume charge density. So Coulomb's law, what is Coulomb's law? Coulomb's law tells you about the force between 2 point electric charges. It simply says that the force of attraction or repulsion between 2 point electric charges is directly proportional to the product of the charges, inversely proportional to the square of distance between them, and acts along the line joining the two charges. Strictly speaking, Coulomb's law applies to the stationary point charges. Here we assume that there are 2 point charges Q1 and Q2 separated by a distance r. Then the force of interaction between these two charges, may be attractive or repulsive, is directly proportional to the product of the magnitude of the two charges, but inversely proportional to the square of separation between the two. So mathematically, we can say that F is equal to K times Q1 Q2 divided by R square, and here K is a constant known as the electrostatic force constant or Coulomb constant. So in vacuum, the value of the K is equivalent to 1 by 4 pi epsilon naught, and epsilon naught here is called the permittivity of the free space. But in the medium, the value of the K is equivalent to 1 by 4 pi epsilon, and epsilon here is known as absolute electric permittivity of the dielectric medium. So the dielectric constant or relative permittivity or specific inductive capacity, as we know, or dielectric coefficient, is given by K or epsilon r, which is given as epsilon by epsilon naught. Therefore, in vacuum, the force is equivalent to 1 by 4 epsilon naught Q1 Q2 by R square, but in the medium the force will be equivalent to 1 by 4 pi epsilon naught epsilon r Q1 Q2 divided by R square, and the value of the epsilon naught here is 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square, and the value of 1 by 4 pi epsilon naught is come out to be round about 9 into 10 to the power 9 Newton meter square per Coulomb square. Then what is the permittivity? The permittivity of a medium is the property of the every material which measures the position offered against the formation of the electric field. That means whenever we apply the electric field into a system or a substance, it always tries to oppose the electric field by polarizations. That measurement, how strongly it opposes the electric field, is known as the permittivity of the medium. Now, coming to the 5 points that has to be remembered from the Coulomb's law. First, the Coulomb's law holds good for the point charges relatively at rest. Coulomb's law is basically experimental law. Coulomb's law is applicable for the microscopic distances as well as very small distances of the order of 10 to the power minus 10 meter. And Coulomb's law force decreases when the charges are placed in a medium other than vacuum. The Coulomb force between the two charges is not affected by the presence of other charges, hence Coulomb force is a two-body interaction. This is all about the Coulomb's law. Now coming to the relative permittivity or dielectric constant or specific inductive capacity or dielectric coefficients, we know it whenever we place two electric charged bodies nearby, they will experience a force among them. This force may be either be attractive or repulsive depending upon the nature of the charge of the two bodies. That means the like charges repel and unlike charges attract to each other. The value of the force acting on these two nearby bodies can be formulated by Coulomb's law. And the force acting between them nearby electrically charged bodies depends upon three main factors. The charge of the bodies Q1 and Q2 in coulombs, that is the product of the two charges of the body. Second one is the distance between the center of the charges. The force is inversely proportional to the square of the distances, as we already learned in the Coulomb's law. The third point is the medium in which the bodies are being placed. So the role of the permittivity comes in this third point, that is, it is found that the force acting between the nearby, the same charged bodies separated by the same distance is different in different medium. For the equation of the Coulomb's law, we find that the force acting between nearby electrically charged body is inversely proportional to the term epsilon naught and epsilon r. This term is called permittivity of the medium. Here the epsilon naught is known as the absolute permittivity of the medium, and epsilon r is the relative permittivity of the medium in which the bodies are placed. The relative permittivity is defined as the ratio of the actual to the absolute permittivity of the medium to the absolute permittivity of the vacuum. If the permittivity of the medium is epsilon, then the value is K equal to epsilon by epsilon naught. The dielectric constant or relative permittivity or specific inductive capacity or dielectric coefficient can also be defined as the ratio of the electrostatic force between two charges separated by the certain distance in vacuum to the electrostatic force between the same two charges separated by the same distance in the medium. Therefore, we can write the K or epsilon r as the ratio between the force in the vacuum divided by the force in the medium when we place the two charges of the same magnitude, in the one in the vacuum, another one in the medium with the same separation. The ratio between them will be known as the dielectric constant or relative permittivity of the medium. This value is a unit length and has no dimension. What about the continuous distribution of charges? So whenever we say the charges are distributed, they are distributed over the surface of the conductor. Any charge which covers a space with a dimension much less than its distance away from an observation point can be considered as point charge. A system of closely spaced charges is said to be form a continuous charge distribution. It is useful to consider the density of the charge distribution as we do for density of solid, liquid and gases, etc. First, we discuss with the linear charge density. That means the charges distribution over the length or in a line. So if the charge is distributed over the straight line or over the circumference of a circle or over the edge of the cuboid, that is, the distribution is called the linear charge distribution. Linear charge density is the charge per unit length and its SI unit is Coulomb per meter. Here we consider the charges are distributed over the line and we take a small elemental length of dl covering a charge of dq. Then the linear charge density lambda is given by dq by dl, and total charge enclosed by all the charges in the system will be given by integral over this lambda dl over the length. And for the surface charge density, when the charge is distributed over the surface area, then the distribution is called the surface charge distribution. And the surface charge density is the charge per unit area and SI unit is Coulomb per meter square. Suppose we have a surface charge distribution and we enclose certain small elemental length enclosing a certain charge dq over a ds, then sigma, which is denoting the surface charge density, is given by dq by ds. And over the charge over the surface, how much charges will be accumulated will be given by the integration over sigma ds over the surface. Same way, the volume charge density, the charge density rho, is given by the surface charge distribution over a volume. When the charges were distributed over the volume, it is given by rho, and rho is given by dq divided by d tau. D tau here is a small elemental volume which is covering the charges. I hope you understand the topic, and in the next topic we will discuss about electrostatics too.